and we are a little bit late to start the second session. So may I request the hydrodynamic interaction effects on tug operations within the midship region alongside large ships. The authors are Jayarathne, Leong, and Ranmuthugala, and the presenter is Mr. Jayarathne, a PhD researcher from Australian Maritime College, the University of Tasmania. His PhD research in ship-to-ship interaction effects simulation. Furthermore, he is one of the permanent staff members for the Department of Marine Engineering, Kottala Defence University, and currently he is on study leave. So may I invite Mr. Jayarathne to present his paper.
Thank you. Good morning to all of you. Thank you very much for the introduction, sir. First of all, actually, I would like to give you some brief idea about the topic. With that brief idea, actually, you will go or you will flow through the presentation. So at the end of the presentation, you will really know what I am talking about. So that's what the idea is. So first thing is interaction, what it is. So we call interaction. People, you hear about interaction, but you should know what interaction means. So interaction, actually, you really feel when you drive your car on a highway. So when you drive your car on a highway, as you see in this picture, when a large vehicle or truck or something will pass by you, you feel like some shaking. Okay, so at that time, you feel sort of effect on your vehicle, which is due to the movement of the other vehicle. So that can vary with a number of factors. So people actually doing research on these sort of interaction effects. That is coming under aerodynamic interaction. So that is aerodynamic interaction. So aerodynamic interaction occurs due to this dynamics of the air. So for these vehicles, that depends on the size of the vehicle, speed of it, and the distance between two vehicles. If you are moving very close to the other one, then you feel more force or movement close to the other vehicle. So you can see that in this picture, people did research about this interaction, aerodynamic, and you can see these curved ones, arrows, are for the movements. These ones are for the forces. So the arrow goes towards the large truck is the sway. The curved one is for the yoke. And definitely you will have one against your direction, which is drag. Okay, so basically you feel number of forces. So far we are talking about aerodynamics. So aerodynamic guys, aeronautical guys know better than me these things. Now when we come to the hydrodynamics, so this is the case with the ship. So it is similar, but we don't feel it because we don't drive tugs or vehicles, ships. We just drive cars, that's why we feel aerodynamics. Now when we go to hydrodynamic case, it is different. And also the problem is, the effect is much larger, not like aerodynamics. The reasons are, you feel more effects due to this compressibility of air and water has different compressibility, and the density of the water, and also ship size and sea state. Those things are prime factors, but they are not the other reasons. Due to these factors, actually, the effect that the other small or the vessel which is moving next to the large vessel feels more effects like surge, sway, and yaw. So we have to study this one because for drivers, okay, we can just put our car on the road and we can just drive and practice those things. But it is not safe though. But we have drive simulators also. But for ships, actually, we can't practice that when we go to sea. We have to practice it on shore. So to practice that, we need to have simulators. Simulators should nicely produce this effect, accurate effect, for them to train while doing simulation. So in my work today, I'm going to talk about just one case I'm doing to calculate or investigate hydrodynamic interaction of a tugboat which is moving close to a large tanker or large ship. tug is kept at the midship region of the large ship and drift angle change. Drift angle is the angle between the center lines of tug and the large ship. So when you have both parallel, your drift angle is 0. You can have different drift angles because tugs obviously they should have different drift angles during the operation. So at AMC we do this research to find out these interaction effects. So to do that, actually we use CFD simulations and experimental investigation, which I am going to show you shortly. So in CFD simulations, we just model similar cases in CFD software to determine these hydrodynamic interaction forces and moments. So you can see two different cases actually. One is this is quite large tug and this is small tug with a tanker. So different tugs. So this is the case actually which we are talking today. So for this CFD I used star CCM. I think you might have heard about star CCM. So star CCM software I used to generate this mesh, and then we did the grid independent study. And after that we found out there is a continuity service the one which can use us good result. So we used that and we started our research with that. So now the problem is we can't rely only on CFD, as our professor explained yesterday. The problem is actually if you get just one result from one mean, you can't verify or validate. So to do that, actually we do validation test using model experiments at the AMC's towing tank. So we replicate same cases. I mean CFD and both the model experiment should be same, and we use same chip models. And we keep it at same location and same angle and same distance and same. If it is scaled, we scale it properly. So we do it like that to validate CFD results. So once we validate, we can use that CFD mesh to extend or expand our research context because our CFD model is valid. So once we do that, now this is the results you see in my paper. Once you get the paper, you can see that. So I'll show you this one by one. So this is the 0-degree drift angle. So this white space belongs to the tanker and the small white term is for the tug. So as you see in this one, you can see this high pressure region of the tanker, bow area, which is in red color. And also this is also positive pressure, but that pressure is slightly, it is lesser than the bow pressure, that's why we have resistance force. And also in this region, I'm not sure if the color is blue or not, but it is blue color actually. It is negative pressure. So not like ordinary tugboat, when it is operating near another vessel, it is operating in different pressure fields due to the existing large vessel. So in this case, this is operating in low pressure region, and also in fact, if you look at the tugboat, it also has this positive and again positive here and negative pressure here. So when these pressure fields interact with each other, tug feels different effects. Different surge force, not like free running tug when it is moving next to an angle. Surge force, sway force, and your moment. Moment is the turning effect of the tugboat. So these things will be different. So here is the first case when this is drifted by 15 degree drift angle. These two center lines now 15 degrees drift angle. You can see this pressure field change now. So you feel different suction towards the tanker. Because this dark blue is for negative pressure. So negative pressure will definitely suck towards the tanker, and it may bang on the tanker if tug master does not know how to handle it. So when you go further, at 30 degrees, it is again different, and this is 45 degrees. Let's see how it changes. At 60 degrees, so this is 75 and this is 90 degrees. And at 90 degrees, you can see leeward side pressure is very low. Negative pressure. But the pressure between bow of the tug and the tanker hull is quite ordinary, not like here. Here if you see, between these two, you have negative pressure, but here leeward side pressure is much dominant. So you feel more drag when you try to move in this direction. You will feel more drag. So this is the CFD pressure plot. So then what I did was, then we plotted these things in a novel plot called HIRP to find out where it is the safest location for this tugs to operate. So this is for the surge force, and it is having maximum surge force at 90 degrees. This is the drift angle, and this is the tugboat, and these are the values. So when you go further, this is sway force. You can see sway is maximum at 45 degrees. So if you are coming at 45 degrees towards the tanker or the large ship, you will feel maximum sway force. And when you go further, this is the yaw moment, again it is 45 degrees. So basically, by looking at this, we can understand that the region from 0 to 50 and 75 to 90 are quite safe for tug to approach a large ship. But in this area, it is quite dangerous because you don't know what type of force you are going to face. So, with that, now I can just come back to the topic. You can see that hydrodynamic interaction. Now you know these two terms. Hydrodynamic interaction. Then hydrodynamic interaction. Effects on tugs. You know definitely. Tugs operating within the midship region. I showed you midship region. Alongside a large ship. So that is our research I did with my co-supervisors to find out the hydrodynamic interaction effects acting on tugboat when it is operating near the midship region with different drift angles. So this is all about presentation, and also in addition to that, I'll just show you quickly, if I get just 30 seconds or something, one video of our model experiment. Sorry, that's not. So this is the setup actually. You can see this tugboat and tanker fixed over there. Then we have all the load cells and everything fixed on this tugboat because we are not measuring the forces on tanker. Only we fix attach all the load cells on the tugboat. Then we pull it to the similar speed. We tested in model experiment CFD. So we can then measure the forces acting on this tugboat. And validate our CFD results. So that's where we need to do experiments and CFD together to get validated, verified and validated results. So since tugs are operating very slowly, you don't see the fast moving vessels, and also scale factor is there. We have to consider all these things, and so this is the speed I tested for one of the tests. Okay, that's it. Thank you very much.
Now we can see the scientific interpretations of these interactions. I think in the past, these experienced tug masters may have been doing it with their experience of handling the tug in a large ship. Okay. But anyway, we will spend 5 minutes on questions.
By doing such a study, how much economical, or what are the gains that you get?
Yeah, actually, the thing is, simulators worth billions of dollars.
Yeah.
So people need to do research and develop these simulators. So these guys will spend money to develop new algorithms, improved ones.
Yeah.
So
No.
then once we put that into the simulator,
Yeah.
then the training, people who train using these simulators definitely get trainings. Is that
Can you economically value that training
Yes.
compared to the cost of the simulators?
Yes. Simulator comes with whole package. So the algorithm is inside the simulator. So definitely it's worthwhile doing that. Otherwise, if you are not developing your simulator, then the problem is other people will do research and they will develop their simulators, and you can't compete with us. So regular research and development is required.
One thing is the practical use of this research. How will and what new machinery systems or automations can come into the tax? Considering this kind of research and analysis.
Yeah.
What automation and autopiloting and those things, can it be possible with this research?
Yeah, actually, let's say for tugboats we don't need to have dynamic position, But if you are going through such research, actually some of my colleagues are doing research for DP operations and all the other stuff. So they investigate similar cases to find out the forces and movements on the ships to improve the DP systems. As an example, post-work DP system, let's say. So they want data, so we can just generate things. That sort of industry-university collaboration, which is a bit lack. I'm also from some member here, but in Sri Lankan university system, it is a bit lack, industry university collaboration. Yeah.
Any more questions? One more question. How is the correlation between your mesh star CCM analysis and the actual result that you obtained from the tank itself? How was the correlation?
Actually, the difference is less than 10%.
Right.
Given the CFD and this one. And definitely we need to do uncertainty analysis for both cases to get the accurate results. So once we do uncertainty analysis and everything became less than 10%. So it definitely gives a very good result, but depends on the effort you put.
Right.
Yeah. So we had to put a lot of effort to do, get proper CFD and model experiment setups and all these things takes time.
Thank you very much.
Thank you.
So, thank you very much, Emma. Thank you.